plan today is to talk about what quantum computers are, how people are building them, what they can do, what they can't do. They're not all powerful, godlike devices, so they do have limitations that we'll get into as well. Okay, without further ado, let me introduce our esteemed panelists. Our first panelist is a mathematician, computer scientist, physicist, expert on quantum information theory. She was a professor at Tel Aviv University and a researcher at the CNRS in Paris. Please welcome Julia Kempe. Our next participant is the professor of quantum mechanical engineering, that's a thing, at MIT, director of the Keck Center for Extreme Quantum Information Theory, and hopefully he'll explain why it's extreme to us. Please welcome Seth Lloyd. Next up, our next guest comes to us from the Air Force Research Laboratory in Rome in upstate New York. She's a senior research scientist there and the primary investigator for the Trapped Ion Quantum Networking Group. Please welcome Kathy-Ann Soderberg. And finally, coming to us from IBM in Yorktown Heights, just north of the city, is the manager of the Experimental Quantum Computing Group, a distinguished research staff member. Please welcome Jerry Chow. So, Seth, let me turn to you first. Quantum mechanics, weird or just unfamiliar?
Definitely weird. I think I prefer the word funky, actually.
Okay, so you heard it. This is the official terminology.
It's the James Brown of sciences.
So how so? I mean, why, and particularly in terms of computation, what's the special quality of quantum physics?
So in quantum mechanics, things that we think of as being like particles, like basketballs or soccer balls, have waves that are attached to them. And so, I've got this ball over here and it's got a wave, and then like I have the ball over here and it's got a wave. But the funky thing about that is that the waves can add up. So I can have a ball that's both here and there at the same time. And if you map this to a bit in a quantum computer, so this is 0, ball over here, ball over there is 1, then I can have a quantum bit or qubit that's 0 and 1 at the same time.
So Julia, why would that be something you would actually want?
Why would this, I want to actually comment on the weird first, if I may.
Funky, please.
Funky. Because I think it depends on your point of view. Coming at it as a physicist with a lot of training in classical physics, it's indeed probably very weird. But if you look at it as a computer scientist, it maybe becomes less weird because we are not spoiled. Our intuition is not, how can I say, biased in any way. And I view it as something which is like probability theory, except the probabilities can be negative, or they can be even complex, but that is not so essential. And so in that sense, it's not very weird. It's just it requires a bit of getting used to, but it's pretty natural. And so for the qubits, why is it useful to have qubits in being both 0 and 1 at the same time? Because if we have many of those, we can think of having various states at the same time, and we can think of computing all these possibilities at the same time. So that leads us to this massive, what's called quantum parallelism.
So Jerry, can you walk me through like just a quick numeric example of, if you have a certain number of qubits, what that means in terms of parallelism?
Yeah, so I mean, one of the, as has been mentioned with regards to these qubits, you have these superpositions. And so you might have some number of bits, but instead of bits now you have qubits, right? And in terms of this parallelism, what you're going to actually have is access to a much larger space of possibilities. So if you have n qubits, you actually have, using these principles of superposition and entanglement, you have access to a space of up to 2 to the n possibilities. And so that type of exponential space gets really, really large for rather modest numbers of qubits. In fact, if you get to around n of 300 qubits, you actually have some state space that is greater than the total number of particles in our universe.
Kathy-Ann, walk through an extremely simple numerical example. Suppose in fact, we do have, but to take an example, 2 of these qubits. Mm-hmm. What does that mean in terms of the computational space that we can work with?
So if you have 2 qubits, you have a 4-qubit state space, because you can have each one stored as a 0 plus 1, and the other one stored as a 0 plus 1, so you get 0, 0, 0, 1, 1, 0, 1, 1. Whereas classically, you could only have 0 or 1. You can't have anything in between.
So the computer's, in a sense, in all possible computational states at
Yeah,
once.
that's right.
Now, Seth, on the face of it, that doesn't sound like such a good idea because you want to get an answer from the computer, and it's just basically telling you everything.
Yeah, and indeed, it's kind of dangerous. If I have a quantum bit that's 0 and 1 at the same time, and I say, yo, are you 0 or are you 1? Well, I mean, you okay, so it's an electron that's either here, and I bring up a very sensitive electrometer, and it says, yo, are you here or there? Well, it's either going to show up here, say with 50% probability, or there with 50% probability. So it's just going to behave like something that's generating a random number, which is kind of useful, but it's not, if you actually want certainty for your answers, it's not so great. So the way that these quantum computations work, you set up all these waves and they're wiggling on top of each other, and they're performing multiple computations simultaneously. So you can think of an individual wave, a wave of, say, electron here and not there. That's kind of like a pure tone, like an electron here and not there is like and electron here and there at the same time is, does somebody want to supply the other tone? Julia's looking scared. It's a chord, so it's you get the computational power from the interference, from the kind of symphonic nature of this. So the idea of a quantum computation is you set up all these waves, they make this beautiful music together in this symphonic way, but at the end of the day, you actually want to have an answer that says yes or no, or 0 or 1. And all the trickery and talent goes into making that happen.
So, Julie, is that any problem I care to pull out of a hat, or that my professors give me as a homework assignment, can I turn it into a problem that's amenable to this kind of chord pattern that then reduces to a single pure tone?
That might depend on your artistry, but in general, quantum computers are good at certain things, and we would leave, a lot of other things to a normal classical computer. And of course, you probably all heard of the problem that a quantum computer can solve very well, and that's factoring numbers, very large numbers into primes. And the way it's done, just like Seth was saying, and I was saying, you can think of these amplitudes of a quantum computer as positive and negative numbers. We try to arrange these waves in a way that all the bad answers cancel out, because you can have several ways to arrive at a wrong answer. And what you'll try is have some with a positive amplitude and some with a negative amplitude, and they cancel out. And then you arrive at the right answer, and voila, you get a factor for a very big number. And that's one of the first and most remarkable things that was discovered a quantum computer can do. And I can elaborate on why it's important. Most of you, all of you, I assume, are using credit cards at the machine or over the internet, and you rely on the fact that they are encrypted. And it so happens that modern day encryption is based on assumptions of hardness of factoring or problems of that type. And it's these type of problems that a quantum computer would be able to easily break.
Interesting. Kathy, let me ask you, drill down a little bit more here.
Sure.
So when I think of a computer, I think of it does arithmetic, logical operations. How do you, without going into details, we'll get to some of the details later, but does the quantum computer also have those same elements of it can add, it can subtract, it can do logical comparisons of things?
Yes. Yes, you need all the same similar components to a classical computer to do quantum computing, but the way that you make the gates looks very different than in a conventional computer. And that somewhat depends on the underlying qubit technology.
Okay, and we'll definitely come back to some of the details on that later, but I just want to establish that it's a computer.
Yes.
It has, you look at it, and though it's configured differently, it does have the recognizable qualities of a computer.
Yeah,
Yes.
you could program it in C or
Yes.
Java, and it has just this one additional instruction which says take this quantum bit and put it here and there at the same time. Put in the state 0 and 1 at the same time. So you supplement an ordinary computer language with just one additional quantum instruction, and you're good to go. If you can build the thing, of course.
Which we'll see in a little bit. Jerry, what are we up to just in general state of the art about how many qubits we have, and what does that mean in terms of vis-a-vis a classical machine?
Yeah, so there's many different physical implementations of building a quantum computer. The underlying core of a quantum computer we call a quantum processor, and what you basically need to build a quantum processor is something that follows the laws of quantum mechanics and can have this quantum mechanical 0 and 1. And in terms of where we are in experiments, we're looking at building universal-based quantum computers of order of 10 to 20 qubits at the moment. And that's kind of where the state of the art is in the field.
And just for reference sake, 20 bits doesn't sound like a lot, actually, but how does that, what kind of power does that endow the machine with?
Well, that's actually very interesting, is because although you might have 20 qubits, you can actually then have this state space of 2 to the 20 possibilities, right? But how much you're actually able to access that then is determined by your coherence time. So there's a metric known as coherence time, which says how good of a quantum state can you actually keep in your quantum processor. And different types of technologies, varying from superconducting to trapped ions, like Kathy Yen works on, have different amounts of coherence time. And so overall, this type of time times the number of qubits, we try to at least my colleagues at IBM, we've started thinking about a metric for this called quantum volume to kind of describe what is the power of a quantum computer.
So walk me through, what's a quantum volume?
You can basically think of it as how many steps of these logical operations, or these gate operations that you can do, these superposition or entanglement steps, in the amount of time that before all of the quantum information is gone, becomes just classical. And so you have a certain number of steps, and then you have a certain amount of depth in terms of the total number of qubits that are connected to one another.
So Julia, let me ask this of you. If I just have my phone, a classical ordinary computer, and I store information in it, one hopes at least the computer will retain that for a long period of time. Is Jerry saying that actually it decays away, and why would it do that inside a quantum computer?
So the big challenge for a quantum computer is indeed to maintain these coherences, or these waves that are spread over not just 1 qubit, but over the collection of, in this case, perhaps 20 qubits, and what we call entanglement, these correlations at a distance of these qubits. And it is true that this is what nature does on a very small scale when we describe electrons and so on. But it's also true that we don't observe this in our everyday life. I mean, when you have a bit, it's either 0 or 1. And the reason we don't observe it is that once we start interacting with the environment, once this very fragile superposition is being subject to the surroundings, it's being subject to noise, and these very fragile superpositions will start to what we call decohere, so just disappear. And the point is, of course, that we need to be able to address this quantum computer. We need to be able to talk to it. We need to be able to manipulate it. So it has to be exposed to us, to our, to the world in that sense. And so we're living in this trade-off situation where, on one hand, we need to protect this thing. So we would like to just put it in the fridge and never touch it. On the other hand, we have to touch it in order to manipulate it. And this is the big challenge that these experimentalists are facing, to battle this decoherence that invariably comes along with the fact that we're exposed to the environment.
Kathy Yen, you're walking into your laboratory. What would we see, and then walk me through what that represents?
Sure. So I'll talk about trapped ion technology, which is what we work on, and I believe Jerry will talk about superconducting qubits in a few minutes. They're very different technologies, but they're both very advanced right now in the field. So for ions, we trap single atoms, and we hold them. They're charged, so you can hold them using electric fields. So first we prepare a vacuum chamber, because as you just heard, these systems are very fragile, so you need to protect them from the environment. So these trapped ions operate at room temperature, but we hold them in a vacuum chamber at roughly 10 to the minus 12 torr. That's the same vacuum as outer space. So the only thing in there is the atoms that you want to manipulate. And you have a neutral atom source, which is just a piece of metal in a stainless steel oven that you heat up, and then that creates a beam of neutral atoms, which you can put near what's called an ion trap, which is just a collection of metal electrodes. Because as I said, we trap these using electric fields since they're charged. So you put an oscillating electric field on that trap, and what that looks like to the atom is a rotating saddle. So then that looks like a bowl. And if you drop a marble in a bowl, eventually it'll come to rest at the bottom of the bowl. The trapped ions do the exact same thing in these potentials. And so we shine the neutral atom beam near the trap, and then we have a laser that actually rips one of the electrons off the neutral atom, and that makes our ion. So that leaves it charged. And at the same time, we have to shine a different color of light in, because coming straight out of an oven, the atoms are essentially screaming hot. And the trap potential just can't catch an atom that's going that fast. So you have to cool it down a little bit with a laser. It's laser cooling. And then that allows you to trap it in this bowl-like potential. And then we shine yet another color of light on the atom. And all these different colors of light create different transitions within the atomic structure. So if you could look in the atom, you would see different energy levels inside. And each color of light is resonant with a different energy level. And so the detection light, when we shine it on, it hits a very strong transition in the atom, which excites it from its ground state. So the qubits themselves are held in the ground states of these atoms. There's 2 ground states. And it sends it to an excited state. It's a very short-lived state. And when it emits a photon. And it does, since it's a strong transition, it does that hundreds of thousands of times. And then we collect those photons on a camera. The ion that we're using is ytterbium, so it emits in the UV. If it was a visible color, you could actually see it with your eye. It'd be a tiny speck in
So
the
wait, hang
vacuum
on.
chamber.
You can see atoms.
You can see atoms.
See atoms.
Yep, just like if
What do
you
they look
shine, just like when you shine a flashlight on a ball in a dark room, right? It scatters light, and then your eyes can see it, and you say, "Oh, there's a ball sitting there."
You're actually seeing-
the atoms do the same thing. They emit photons that if your eye was visible to the UV, you could see them. It would just be a tiny dot on a very dark background. Like
So you can see a single atom fluorescing.
the
Wow,
darkest,
that's pretty cool.
the brightest star on a very dark sky. Unfortunately, we can't see it in the UV with our eyes, so we have to use a camera. But if you were to walk into our lab, you would see large optical tables that are about 6 feet long by 4 feet wide, filled with lasers, because to do all the different operations, you need different frequencies of light. And then you'd see another vacuum chamber another optical table, that holds our vacuum chambers.
Okay, so let me just see if I follow.
Yep.
You load your system
Yes.
with ytterbium ions.
Yes.
And to perform a computation, just for example, how do you clear the memory? What would be the first step in your computation?
Sure. So usually you start with some number, let's say between 2 and 5 ions is what you would want. So you load 2 or 5 ions, let's say 2 for this example. So we can turn the oven on for a set amount of time, and we shine the laser that rips the electron off to create the ions. And we wait till we get 2 ions. And then we can see them on the camera. And so we initialize the system to a 0 state, just like in conventional computing, you have to initialize your computer to a 0 state. And then if we wanted to put those 2 ions in a superposition, we could shine either a laser or a microwave at them, and that would create a superposition. So you could think of qubits on what's called a block sphere, which is just a unit sphere, where the up z-axis could be your 1 qubit state, and the down z-axis could be your 0 qubit state. So you prepare it in a 0, and then we shine these microwaves or lasers on the atoms, and it causes the population to rotate, basically. And so you just stop when you get to the up state, and you can look at that. It's a trace on a scope.
So for example, I mean, a standard operation, simplest possible operation you might have in a computer is just NOT.
That's right.
So how would you do a NOT? Just
So
can
yeah,
walk
you
through
would
that?
prepare your qubit in the 0 state, and then you would shine a microwave or a laser beam on it for a set amount of time, and it would cause the population to evolve to the up state, and that's a NOT gate. If you go from 0 to 1, that's a NOT gate. If you
And
left
it
that light or microwave interaction on, then it would go back down to the 0 state, and it would just keep rotating.
So suppose I want to do something a bit more sophisticated, like an AND or something that actually combines 2 qubits. How would you do that?
Yeah, so if you had 2 qubits in trapped ions, the nice thing is that because they're charged, they want to repel each other, but because there's a trapping potential on them, they get pushed together, so they find a happy medium where they sit. But they have a shared motional mode due to this interaction. So they're a lot like a Newton's cradle. If you pull a ball on a Newton's cradle, you see all the balls move
And it goes
together. Yeah, that's right. That's right. And so the trapped ions do the same thing. If you start to shine a laser beam on one and you excite some motion, and it actually excites motion in both ions. And so then you have a data bus that you can get the ions to talk to each other. And if you had 5 ions, you could actually use this data bus to get 1 and 5 to talk to each other directly. So you're not limited to nearest neighbor interactions in the trapped ion system.
And you can use that to combine
That's right. And
data.
then you can use that combined motional mode to get the qubit states to talk to each other and create things like controlled NOT gates, say.
Great. So Jerry, can you kind of repeat that kind of virtuoso performance
Yeah,
for your own lab?
I'll try my best there.
It's going to be hard, I know. What's it like in there, actually? Just
Yeah, so our lab looks a lot different from what Kathy Ann described. and that the reason for that is because the underlying qubit is very different. One difference that the main difference is that instead of actually having physical, naturally occurring qubits, in this case ytterbium ions, that you can, all of this work is based off of having really, really stable atomic clocks. What we're doing with superconducting qubits is to actually engineer and build them on a chip. So it's different. It's a little more integrated. You're actually using lithographic techniques that you know and love today with your silicon processors, and instead of the materials that are in your chips that are in your phone or your laptop, we're using slightly different materials to build superconducting circuits. So superconducting refers to materials that when they're cold, they have basically no resistance. And by using the right kinds of superconductors, you can actually build quantum effects into circuit elements.
So with Kempe, I have a good picture for what the bit is. The ion is either pointing up or rotating in that direction that corresponds to up or the other way. So what's the corresponding?
Yeah, so the way to think about it here is that you're actually building an oscillator circuit. So if you go back to your electrical engineering days, think about the circuits that you might build with resistors or capacitors or inductors. These are various circuit elements. In the case of a superconducting circuit, you actually can use an element known as a Josephson junction. And a Josephson junction is basically a sandwich of aluminum, aluminum oxide, aluminum. And what's phenomenal about this element is that you can combine it with a standard capacitor, and you can make it oscillate in the microwave regime, so around 5 gigahertz. And choosing the right parameters of the capacitance and this Josephson junction, you can isolate it to build a qubit state, so 0 and 1, that resonates at around 5 gigahertz.
So in your case, can you walk through an example? You load your computer.
Right. So in this case, we have a silicon fabrication facility that builds these circuits. They come out in large wafer form, and then we have to cut them up into smaller chips. These chips are packaged into a printed circuit board, like what you might see inside your phone. But this printed circuit board carries microwave signals, and so the printed circuit board then needs to be cooled down to really, really low temperatures to basically have the qubits function properly. So I said that we use these superconducting materials. And so the materials are niobium and aluminum. And for them to superconduct, and for there to be so little noise that we can actually see these quantum mechanical effects at 5 gigahertz, we need to cool down to 15 millikelvin. So that's, since you already brought up the space analogy, it's colder than outer space as well. In fact, with the microwave background in space, it's around, it's a little under 4 Kelvin there. But we're getting down to 15 millikelvin.
Wow.
Right? And so the refrigeration systems that we build, that we use, they're commercially available, but it's phenomenal that you can just hit a button, turn a key, and cool down these devices to such a low temperature.
In the example of the trapped ions, if you want to execute a NOT operation, you hit it with lasers or microwaves. What do you do in your case?
Yeah, so in this case, it's more electrically controlled. So you're placing this chip inside of this printed circuit board. It's inside of the dilution refrigerator. But then you have all these wires that come down through the refrigerator, and those carry electrical signals. And so to do, say, a NOT operation, what we're doing is basically applying a shaped microwave pulse that's generated at room temperature, so on a set of electronics that sits outside of the refrigerator. We generate a 5 gigahertz signal for a certain amount of time, say maybe 20 nanoseconds or 30 nanoseconds. That pulse gets sent down into the refrigerator, applies just enough energy to flip your qubit state from 0 to 1.
Okay, and then you could do, how would you do an AND or an NAND?
Yeah, and then with regards to 2 qubit gates, so our particular architecture connects qubits on the chip. So there's other microwave circuitry that are used to define particular interactions between qubits on a chip. But then those interactions are again activated using microwaves. So just the way that we do the NOT, we might send pulses at a slightly different frequency down into the refrigerator to induce a 2 qubit operation, such as a controlled NOT gate.
So everything you've described is acting on the system. So how does the system act on us to return its information and the result of the computation?
Yeah. So in the case with Kathy Ann, they're sending another laser beam to do the detection, and you can see it with the camera. But with us, what we actually have to do is send another microwave pulse, which is resonant with a detection cavity. So there's actually a resonator on the chip that oscillates at a slightly different frequency depending on if the qubit is 0 or if the qubit is 1. And so we interrogate this cavity with a microwave pulse, and at very low energy levels, so single photon energy levels at say 6 gigahertz. And so that signal goes down into the fridge, gets amplified through various stages, and then we basically have to digitize it to determine whether the qubit was a 0 or 1.
Cool. Seth, just to kind of bring some perspective on the technical discussion here, what would be some pros and cons of the different techniques? Why would you use strapped ions in some cases, in superconducting qubits, and others?
Well, so pretty much anything at the microscopic level will compute if you shine light on it in the right way via either lasers or microwaves. But some things compute better than others. So what's been happening over the last decade and a half or so is that the technologies for instance, superconducting quantum computing have really advanced by a lot. I mean, I was participating in the early experiments to build the second superconducting qubit around 2000. It was a so-called flux qubit. In these supercurrents, you have a little loop interrupted by a Josephson junction. And so supercurrent going around forever that way, you call it 0. And supercurrent going around forever that way, in clockwise for you, then you call it 1. And then, supercurrent going around both ways simultaneously, both clockwise and counterclockwise simultaneously, that's 0 and 1 at the same time. So that's how you get a quantum bit in these things. But you would let them sit for a little while, and then they'd get kind of completely randomized very, very rapidly. And so these original superconducting qubits were, well, they sucked, let's face it.
That's a technical language.
That's a technical term. It's like funky, right? So, but then there was this great innovations, actually, which Greg participated in. I think this was part of your PhD thesis, was developing. People thought, oh, the materials are bad, something's wrong with how we're building these things. But it turned out that it was really much more a kind of a design issue. And by being really sneaky about how you design these systems, you could make them much, 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 much more coherent, so that they could, they could oscillate around or could perform 10,000 logic operations before these things got messed up. And so with superconducting systems, I think that what you did in your PhD thesis and afterwards was a really amazing innovation. And then which also allowed to because you're building them on these chips, you can put many of them together. So there's a clear path towards scalability. Similarly with ion traps, the first ion trap experiments were done in the mid 1990s, but they were 2 qubit experiments, sometimes 2 qubits. You can still do interesting things with 2 qubits, right? You can search a data space with 4 possibilities, and you can find, is it here, 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 by only looking once. Like, how can that be classically? But quantum mechanically.
We're about to find out actually in a little while.
Yeah. So what's happening is that there's been also with ion traps, there have been all these advances in integration and making ion traps larger and larger, integrating them with quantum communication lines. So there's been a steady advance in constructing more and more elaborate and complex quantum information processors. Ion traps and superconducting systems are the 2 technologies that are furthest along the way, but there are a whole bunch of other technologies like nitrogen vacancies in diamond, and topological systems, and all kinds of crazy things, because again, pretty much anything will compute. And even though, as Jerry was saying, the 20 qubits, okay, that doesn't sound like a lot, but 2 to the 20 is about 1 million. 2 to the 30 qubits, 2 to the 30 is about 1 billion. 40 qubits, that's 1 trillion. Well, now you're starting to try to manipulate these 1 trillion numbers, 1 billion or 1 trillion numbers, and actually that becomes very difficult classically. So the devices that are being built right now are just at the threshold where we actually can't understand what's going on inside them classically. Previously, we were able to simulate what was happening on a huge, humongous classical computer and try to figure out what's going on. Now we're kind of on our own. It's sort of exploring this quantum frontier, and we are going to be able to try to figure out what's going on in them. And then the hope is that when we build these devices, we can use them to build ever larger devices and build, quantum computers that have 1,000 qubits or 1,000,000 qubits or 1,000,000,000 qubits.
So, Julia, if the machines, and it's a great moment to be in historically, that the machines are now crossing over and exceeding the power of our most powerful classical computer. But then how do we know that they're working properly if we can't even compare the result of the calculation of a quantum computer to a classical computer anymore?
Working properly. I mean,
Because I don't know about you, but my computer crashes sometimes.
I mean, how can we ensure that they're working properly is maybe a question I can answer, because as you asked, what architecture will eventually win or be the best one, and of course the question we need to answer is which one scales best to a large number of qubits. And in theory, I'm a theoretician, so I'm in the position where I write my papers saying, let's assume we have a quantum computer of 10,000 qubits, and then, but there is a lot of theory developed, a theory of, say, of quantum error correction, for instance, where we face the fact that no matter how well Kathy Ann and Jerry perform their jobs, the elements out of which they build their quantum computers will be faulty at some level. There will be a probability that they'll fail, that they'll lose their coherence, and so on. And there actually is a very beautiful theory of quantum error correction that once we are above a certain threshold with the noise in their systems, so once the noise is small enough, then we can actually build in redundancy into these qubits in a way that the computation will perform flawlessly. And that's a very nice theory that will then allow us to make the quantum computer work at a larger scale.
So it can fix the mistakes that
it can fix the mistakes, yes.
So I think this might be a good point to talk about how they actually work. And Jerry, I know you've got a demonstration you'd like to present to us.
Well, first, the way that I want to actually motivate this is based off of this search a search algorithm, and it's and Seth already alluded to this. But let's say that you have 4 cards, right? And you play the game of Monty, right? You might go to a street corner somewhere and put
Not
some
that
money.
we're advocating you do that.
Don't do that.
And so out of these 4 cards, you've got one of them which is different. One of them is a queen. And now we're going to flip them over, and when you play this game, you're randomly going to try to find where that queen is, right? So you're gonna try once, and you're going to flip over a card and see whether or not it's the queen. And so in playing this game, you really only have a 1 in 4 chance of getting it right on your first try. But now, what's interesting about this type of game is we can also ask, well, how would we do this if we had a computer? What does a classical computer do with this game, and what does a quantum computer do with this game? Okay, so in the case of a classical processor, what we're doing is when we flip over these cards, you can think of this as storing a database. In this case, we can also call it an oracle. So you store the database with the hidden set of cards where the queen is properly located. With the classical computer, what you're going to do is, in order to find where it is, you're gonna look at all the possible arrangements, right? So you're gonna start with one particular arrangement. Let's start with placing the queen in the first slot, and we're gonna take that entry, use it as an input. We're gonna do some processing, in this case the green box, where you're gonna do some comparison with what's in the database, and you're gonna make a decision at the end whether or not it was correct or not. In this case, it was not correct, and you get a 0. Okay, and so now then you can try the next one, and again you're gonna get a 0, and then the next one, and this time you get it right. But of course, classically you're gonna go through all 4 of them, so after you go through all 4, you see that on average you would have gotten this correct. Basically, you would get it correct after querying this database about 2.25 times, right? So. This problem of search, in this case with the classical computer, you can only kind of do this sequentially or by choosing at random. But with the quantum processor, this is where a lot of the ideas of quantum mechanics can come through. And so in the next slide here, with the quantum processor, you have access to superposition. And so just like we talked about how you can be in 0 and 1 at the same time, what you can do with a 2-qubit system is to make a superposition of all 4 of the possibilities, 0, 0, 0, 1, 1, 0, and 1, 1, to represent all 4 of the possible arrangements of this hidden queen. And so we can take that superposition state, use it as basically as an input, call the database just once, perform some processing step. In this case, the processing step involves entanglement, and it involves this quantum interference of adding together the waves, and it'll amplify the answer for exactly the right answer. And so every time, no matter what you place into the database, wherever you hit that card, using only one call to the database, you get the right answer using this algorithm. And this particular algorithm is known as Grover's algorithm, and it's a simple case that gives you this sense for what is done differently in terms of processing information on a classical computer versus a quantum computer. And so on the next slide, what you actually would do when you want to program an actual quantum processor is to use this language of quantum gates. And so what you see here is actually a quantum circuit. As Seth alluded to the idea of music, we call this actually a score because it kind of looks like a musical score. And the concept of time really, and time with gates really has a strong analogy here because it's like you're playing different notes on these different qubits. What you see here is really just 2 of the qubits being populated with these different operations, which realizes the Grover's algorithm. And to break it down a little bit further in the next slide, what you see is that these various steps of superposition, the stored database, and the actual post-processing steps are all encoded into these various gate operations that you can apply. And in this case, we can actually run it through and get a result. And I can actually launch this live if
Please, by all means.
yeah.
Why are you switching over? Kathy Ann, you were really one of the first people to actually do this for real in your dissertation work. Can you describe what you accomplished?
Yeah, sure. So we did it with trapped ions. We had 2 trapped ions, and as Jerry just showed, that gives you the 4-element database. And what we did in practice was we had the computer mark a state, and then we would run the algorithm similar to the diagram that Jerry just showed. It looks very similar. And then at the end, we would see what the probability was that we recovered that marked state. And at the time, the entangling gate that we used, we were just starting to learn to use it. It had just been demonstrated. And so we found the marked state with a probability of about 60%. But Jerry just told you it should be 100%. And that's because the fidelity, that's one way you can measure how good a quantum gate is, the fidelity of our gate wasn't as high as we would have liked it to be, mostly due to technical difficulties. This isn't a fundamental limit of trapped ions. They've since repeated this experiment with 3 qubits recently, and Chris Monroe's group at the University of Maryland. And they did quite a bit better because the technology's progressed now at this point that these gates are at very high fidelities, near the fault-tolerant levels that Julia was saying earlier that you need to run these computers.
You were telling me earlier that it was so delicate that you could so much as look at the laser wrong and it would give you the...
Yeah, so we used
wouldn't work.
cadmium ions in my graduate work, and they need laser frequencies that are about 215 nanometers, which is an incredibly difficult color of light to generate. You basically have to quadruple a laser to get there. So you take a laser, you double it, and then you double it again. And doubling's hard, and the efficiency is low. And one of the people in our lab just had the right acoustic sound to his voice that he would unlock our doubling cavities. And so sometimes when he came in the room, he would start to talk, and we were trying to run our experiment, and our laser would shut off. They're very fragile systems. We like the laser.
So Jerry, are you ready to go with this?
Yeah,
this
absolutely.
is actually a live quantum computer.
Yeah, and I wanted to start by just showing a little bit about the interface of what we have. So this is the IBM Q experience. And what we actually have is a lot of content on there for anybody to get started with learning how to program and actually use a quantum
anybody
computer.
can do this.
Anybody can log in, sign up for an account. We have this library with various user guides for beginners, if you're more familiar with some mathematics, like linear algebra, and even another guide which actually leads you to our GitHub developer repository. But through this portal, you have access to learning about from the basics of a qubit, superposition, entanglement, simple algorithms such as this Grover's algorithm. And we also have a community board feature where we have the ability for anyone to ask questions and our IBM researchers are more than happy to answer.
Julie, I wanted to go back to what you're saying about the factorizing problem. That's, in addition to the search algorithm, the other use that people always talk about with quantum computers. So what's kind of the state of the art in that? Can you factor the number 15 or get that high even?
You can, I mean, Jerry would probably be a better person, but with 20 qubits, you can imagine that you can factor it, perhaps with some overhead. I would guess you can maybe factor numbers up to 100, which of course you can do in your head. So at this stage, we are really at a level where we demonstrate things when it comes to factoring. The cryptographic systems that I was talking about that your credit cards rely on, these usually have something maybe up to 1,000 bits. So I think once we get a quantum computer to the order of perhaps 1 or several thousand qubits, then you better stop using your credit cards with the current encryption. So
One thing that I would like to mention though with regards to Shor's algorithm though is that because of the error rates that we end up having with the physical qubits, sure, if you have 1,000 perfect qubits, you might start thinking about Shor's algorithm for 1,000 digit numbers, but with needing quantum error correction and a lot of the best known encodings, you have an overhead that significantly pushes that threshold further. So I think that in terms of Shor's algorithm and a realistic Grover's search, you're thinking about probably needing millions of tens of millions of qubits. So
it's a bit further off, but it's still, there would come a day where...
There'll come a day when you got to worry about your bank accounts, but it's the horizon for that is a bit further beyond where we're currently at.
So millions of physical
qubits, yeah. So definitely maybe around a few thousand logical qubits, but the encoding depth is what's going to matter there.
So, Kathy Ann, you were describing also to me earlier that on the one hand, quantum computers take away our privacy by breaking these codes, but they might also restore it. Can you describe some of the work you've done for the restoration process?
Yeah, so there's people are working now on, in addition to quantum computing, quantum networking. And what you can do with quantum mechanics for networking and communication, the easiest example to explain it, it's been around for a while, is called quantum key distribution, where you send a message between two parties, say Alice and Bob, using single photons. And because the photons are encoded using quantum mechanics, you can actually make protocols that are ultra secure. And by that we mean they're tamper-proof, meaning that even if an eavesdropper can't get between Alice and Bob to get the signal because they don't have the corresponding information that was encoded in the quantum mechanics. But even if an eavesdropper were to try and grab the signal, the protocols are tamper evident. And so Alice and Bob would see that immediately when they started to talk about the results that they got, and they would abandon the protocol. So yes, it can do things like break encryption, but it can also provide ultra secure protocols.
So what are you doing in your lab now to kind of bring that into fruition?
So we're working on quantum networking where instead of sending key information, which that just sends information to generate a key and then you would use the key for something else, we and a lot of people in the field are moving towards quantum networking where you actually send quantum information directly over some longer distance link. And so this allows you to do things like ultra secure communication protocols, or people are also looking at it for distributed computing, where you don't just have one computer sitting there with millions, let's say, of qubits, but you distribute these qubits over a larger space, and you have smaller banks of qubits.
Seth, you once told me, this is a couple years ago now, I hope you remember the anecdote, the NSA funded some early quantum computing work to show this wasn't possible because they didn't want to have unbreakable codes. Can you walk through that?
Oh yeah, so I was at the, I back in 1993 I wrote the first paper showing how you build a quantum computer using these methods of zapping stuff with microwaves and lasers and things like that. And then we started to work with people to build them. And in 1994, I think the first U.S. government meeting to discuss funding for quantum computing took place at DARPA in Arlington and Virginia. And during this meeting, there were a bunch of people, including Peter Shore, were there talking about stuff. And a fellow named stood up and he said, "I'm Keith Miller from the NSA, and I am authorized to tell you that the NSA is interested in quantum computing." And then he sat down again.
You didn't have to kill it.
And everyone went, "Oh my God, somebody from the NSA actually told us something. That's incredible." But it caused such a stir that he stood up again and he said, "Well, I believe I'm also authorized to tell you this. Of course the NSA is interested in quantum computing, because our primary mission is to protect the secrets of the country, up to 30 years for top secrets. We have a whole bunch of information that's out there that's already encrypted, which, if someone could build a quantum computer, could be decrypted, and that would be bad." So really, what we would really prefer is that it not be possible to build a quantum computer. By the way, this is a good person to have funding you. It's like, they call up and they say, "How's it going?" And we say, "Oh, it's terrible. The qubits aren't working. Everything's decoherent." "Great, that's wonderful. Here, you're going to give us some more money." That didn't last very long. But then he said, "But because of our secondary mission, if it is possible, we want to have the first one." So.
To bring this back down to more quotidian kind of applications, Jerry, you once described to me some of the molecular calculations you were doing. Can you walk through what you're doing with these molecules?
So I think one of the more kind of near-term areas that we'd like to look at application-wise with quantum computers actually is in chemical simulation. So what's actually interesting is it dates back to Feynman in around 1980s when he actually talked about wouldn't it be great to actually simulate nature using something that follows the same quantum mechanical principles of nature. And there's been a lot of theoretical work going into, well, how would you actually map, say, problems in quantum chemistry, for example, electronic and molecular structure, onto physical quantum bits. And it's a really neat idea in the sense that you can actually try and get an analog for a real physical system, such as the energy levels of, say, a hydrogen molecule, but actually run it on a chip, right? Run that simulation on qubits that's inside of one of our dilution refrigerators. And so our team has done various both theoretical explorations and recently experimental demonstrations of how to do some rather simple molecular calculations. So looking at the ground state energy of a simple molecule, just like hydrogen, so 2 H's, and then lithium hydride, beryllium hydride, but very very small at this stage. But it shows the type of trajectory, if you will, of application in the near term, because at some point with these different molecular structures, you get to a point where there's too many electrons in it that it's impossible to, again, simulate it on any classical computer. And it can be rather modest molecular sizes that already max out all the supercomputing resource in the world. And there's a lot of potential there for quantum computing to really be a game changer in that field.
Seth, I was wondering if you could merge for me the two great computing tasks of our time, machine learning and quantum computing. Is there a relationship between the two?
Yeah, there's the only way to get information right now is to, the only way to get a grant right now is to apply to do something with big data and machine learning. And then in physics, the only way to get a grant is to do something with graphene. So the material of the future along with gallium arsenide. So the real reason is to have something so you can have a grant that's, graphene-based quantum random access memories for the analysis of big data. It's a winner, I guarantee it.
You heard it here.
So it's interesting now that we actually are about to have simple quantum computers that have tens of qubits and say 50 qubits coming up, and I think that there's a reasonable path to think of having up to 1,000 physical qubits over the next 5 to 10 years. I don't think that's an unreasonable to expect. What will you do with these devices? Now, because they are quantum mechanical and they're very hard to simulate classically, as Jerry was saying, Quantum mechanics, it's famously weird and funky, and quantum systems exhibit funky and strange effects like entanglement and Einstein-Podolsky-Rosen correlations and Schrödinger's cats and statistical patterns in data that are very hard to capture classically. They're counterintuitive. It's hard for classical computers to capture them. So if they can exhibit these, if quantum systems can generate these funky patterns that you can't generate classically, maybe they can also recognize patterns that you can't recognize classically. Now, machine learning is about taking patterns in data and trying to tease them out and show that they're there. It's recognizing patterns in data. Machine learning is, of course, very trendy right now, justifiably so. Not really because actually I think it's about to supplant human beings or anything like that, but because actually it's gotten good. There's this thing called deep learning, which when I learned about it like 3 or 4 years ago, I said, "Wow, this is fantastic! Computers will tell us about love and truth and happiness and all this deep stuff." But no such luck. It turns out that these are just electronic analogs of neural circuitry that have many levels in it. So they're deep in that sense. But they actually do problems. They solve problems that are hard to do. Now, if you get inside a machine learning algorithm, like say the Netflix algorithm, where you say, "Okay, what shall I watch today?" and Netflix says, "Well, I think that you would like to see Dirty Harry." But no, for some reason, my students don't watch Clint Eastwood any longer. I don't know what it is. But what Netflix is doing is they're actually looking at the preferences of everybody out there who's looking at Netflix, comparing your preferences to theirs, and then doing what's called a matrix completion algorithm to recommend something to you. Now, if you were to program that into a quantum computer, it turns out that their algorithm, which they run it twice a day because it's so incredibly computationally intensive, that if you were to do that on a quantum computer, you could have a quantum computer that had, say, 100 quantum bits, and you could do 10,000 operations, and it would do the same set of operations in a quantum mechanical fashion. So we decided, hey, this is great. We'll call this the quantum Netflix algorithm. But then I Googled quantum Netflix algorithm. It turns out that Netflix calls their own algorithm the quantum algorithm, even though it has nothing whatsoever to do with quantum mechanics. So using quantum computers, quantum systems in general, exhibit strange and counterintuitive patterns. This gives you reason to hope that they can recognize strange patterns. And it turns out that the actual stuff that they're doing already for things like factoring numbers is great for actually finding patterns in data. And actually, this is a nice application that people have been using to demonstrate simple versions of these algorithms on small quantum computers.
Obviously, the world as we know it would not be the same without computers. They're just everywhere. They're ubiquitous. Will 50 years from now people say the same thing about quantum computers? Will they be as transformative as classical computers have been?
That's an excellent question. I think a quantum computer will remain, it might be ubiquitous, but it will remain a special purpose device for various things. I don't think it will replace the computers as we know them in its entirety. So I view the future perhaps as you having your laptop and then a little dangle with one of Jerry's or Kathy Ann's contraptions, and then whenever you need to break into somebody else's credit card or whatever it is that you want to do, you make calls to that to that special device. I think that's more likely picture of the future with a quantum computer in it than, yeah.
So it's more like a GPU inside of an Xbox type of thing.
I guess.
Than a
yes.
It won't be a literally quantum iPhone. Although Apple may trademark that like Netflix and Verizon have been, so we should be
right.
Well, I'm more optimistic. I think if you build it, they will come. Right. So once we have quantum computers to play around with, which we already do, thanks to IBM, and over the net, people will play around and will come up with more quantum apps, QAPs for all.
Did you trademark that word?
I trademarked the cloud with a Q.
Questions?
So the 4-card Monty example, I mean, it looks to me like something that's could basically backwards solve any kind of cryptographic hash, like as a black box for whatever the hash is. And yet I hear about these quantum-proof cryptographic methods, and because it seems like it doesn't matter what the actual hash operations are, how does that, like, what is the general underlying principle for these quantum-proof hash functions?
So a hash function in cryptography is a function that just like scrambles everything up in a way where you can check to see if it's been scrambled up in the proper fashion. And inverting these, so undoing this hashing is supposed to be hard and as a basis for a lot of cryptographic protocols. It's still hard on a quantum computer. That is, this quantum searching will allow you to get a speed up that will allow you to solve some problems that you would be able to solve classically. But this kind of hashing problem is still hard on a quantum computer. So one of the things that's going on right now, exactly because quantum computers are getting more powerful, though let's face it, we're still, we can basically compute our way out of a paper bag now, whereas previously we couldn't compute our way out of a paper bag. So, but even the NSA has issued an advisory saying, if you're going to come up with an application that's supposed to still be secure 20 years down the line, it's time for you to think of something in addition, because quantum computers might be there. So people are coming to try to come up with what's called post-quantum cryptography, and I think that you're alluding to some of these problems there.
Now you make me wonder what post-quantum cryptography could possibly be. Can you just give a simple example?
So based on so public key cryptography is a way where I send I buy green coffee beans over the internet and then roast them at home. So
Which you actually do.
Yes, I do. Absolutely, yes. It's so much fresher that way. I highly recommend this. So when I do this, when I try to buy something from Sweet Maria's in Berkeley, this 10 pounds of Costa Rican, then Sweet Maria's sends me a big number, which is a product of two smaller numbers, which are prime numbers. And this is called the public key, this big number. I can use that number to encrypt my information in a way such that only Sweet Maria, who knows the two smaller numbers, can decrypt it. And that's the basis for public key cryptography. There's a public key, which is what they send out there. Anybody can encrypt. But to decrypt, you need to know the private key, these two numbers.
This is what quantum computers can do.
They can find the private key given the public key, which would be a very disruptive thing because I like my freshly roasted green coffee, and I would be pretty pissed off if I couldn't get it. So the idea is you see this as a rather specific protocol. And so what people are trying to come up with are other protocols where quantum computers can't break those protocols, where there's a public key, you can encrypt using the public key, but then you can only decrypt using the private key, but a quantum computer can't find the private key. And so far there's been mixed success, I would say, about doing this. Nothing's ready for prime time.
I mean, I should say, this is also important because even though a quantum computer is not there, you might want to encode your information in a way that nobody can decode it in the next 100 years. And 100 years is a very long time, right? And then we might assume a quantum computer could be there. I mean, a big one, whatever. And the post refers to the fact that even though you encrypt it today, maybe you don't want it to be decrypted in 95 years by one of the successors of Jerry's computers. And there are methods nowadays, in fact, that cryptographers have started to develop, but they are extremely impractical at this. The public keys you would have to transmit are so long that it would take you hours basically to do that. But it would be wrong to say that there is no alternative, but it's not a practical alternative.
More questions. I saw a bunch.
How does the observer effect play into retrieving information?
Can you elaborate?
I don't know. Well, it seems like if you tried to observe the information, it would collapse, right? It would just collapse back to 2 bits. So how do you maintain the 4 bits or whatever if you're using a 2-bit, 2-qubit process?
Yeah. So it's observing it is essential to how we actually make use of a quantum computer, right? Because it has to be something tangible that we can put in. It has to be something tangible that we can take out. So the input will be classical bits. The output will be classical bits. In between is where we make use of superposition, entanglement, and this 2 to the n exponential space, state space. And the key thing is how do you tailor your algorithm to make use of that so that when you perform that measurement, you've learned something that you otherwise wouldn't have been able to calculate. So it's all about how you define those interferences of the waves through the operations you perform in between.
you only observe at the end. Before that, it's considered to be rude to look at somebody's quantum computer while it's in operation.
So that's part of the difficulty in controlling these very complex systems, is because if you make a measurement, or if the environment makes a measurement without your knowledge, the same thing happens. And so you have to control the system very well so that you only look, or the environment only measures the system at the end of the computation.
So it sounds like a lot of the stuff that you guys are working on is kind of like a straight analogy from a classical computer to a quantum computer, where like a bit is a qubit, and you're working with C0 gates. I was wondering if you could talk about how quantum annealers, like what D-Wave works on, how what you guys work on factors into that, and if there are any sort of limitations using the annealing paradigm, because I know that that's usually better off for like combinatorial optimization problems, but is there any other sort of limitation on what an annealer could do versus what a straight quantum computer could do?
Well, I think the first thing there is just that an annealer is a more restricted type of problem, right? So your hardware, the way that you lay down these circuits in an annealer, you've defined all the couplings between these devices, and you've defined a particular energy landscape that you want to, say, optimize or find the ground state for. And then in the case with the systems that we're building, where you have full quantum control over any of the qubits, you really can drive the system to any kind of quantum problem that you want. And so it's reprogrammable in that sense, right? And you can define your optimization landscape in more generality. But maybe Seth, you can also comment on the D-Wave annealer.
I mean, also let me say that you keep on letting people who possess prior knowledge into this room, which makes our lives harder. So, but fun, what's that about? So, so a quantum annealer, as Jerry was saying, it's actually a very old idea classically. There's a notion called simulated annealing classically, where you want to solve a hard problem. So you want to find, the minimum value of some function. And many problems are like this, like the traveling salesman problem. I want to find the shortest path that will get me through all the cities in the United States and back to where I started. That's a hard problem. And so what you do is you map this problem into finding the lowest energy state of a physical system. And then you try to find this lowest energy state by cooling, annealing, that's why it's called annealing, to get down to this lowest energy state. Now, quantum annealing is a sneaky trick that does this quantum mechanically. You construct a quantum system. I mean, for instance, this D-Wave quantum annealer is a tunable device with up to a couple thousand quantum bits, and they can tune all the couplings between them. And then you set it up so that the lowest energy state encodes the answer to your problem, and then you try to find this lowest energy state by kind of oozing in a funky quantum mechanical state fashion from some known state into this unknown state. And either it works or it doesn't. Now, it's an interesting situation because actually nobody knows if this is supposed to work even in theory. And so it's one of these things where if you build it and then you see what happens, they find that some fraction of the time they actually get the right answer. There's a lot of argument about whether this is happening in an intrinsically quantum mechanical way or not. But I mean, these are very interesting systems. I mean, D-Wave deserves great credit for building a large-scale quantum system. It's got lots of entanglement in it. It's got, it has thousands of quantum bits. And it's actually a beautiful system just for doing experiments on. I'm going to a conference in Japan next week, or 2 weeks from now, where basically people are going to report on all the experiments that they're doing on these different D-Wave devices to try to figure out what the heck is going on.
I'm afraid I'm going to have to cut off the questions there. Thanks to all of you for coming.